What would actually happen if the power grid failed across an entire region? Not just the lights going out, but the water systems, hospitals, fuel supply, and communication networks that all depend on electricity. In the next few minutes, we're going to walk through the real timeline engineers expect during a major grid collapse, from the first seconds to the first several days. In our modern world, electricity isn't just a convenience. It's the invisible foundation holding up nearly every system we depend on: communication, water, transportation, food distribution, and healthcare. But the power grid that keeps all of this running is more than just wires and power plants. It's often called the largest and most complex machine ever built. And like any machine, it can fail. To understand how a grid failure unfolds, we first need to understand how the grid actually works. It is the most delicate balancing act in engineering. The electrical grid isn't a giant battery storing energy for later use. In fact, large-scale storage has historically been extremely difficult and expensive. Instead, electricity must be produced at the exact moment it's consumed. Every millisecond, power plants across the country are constantly adjusting their output so that supply perfectly matches demand. Too much electricity on the grid, the frequency rises. Too little electricity, the frequency drops. In the United States, the entire system runs at 60 hertz, 60 electrical cycles per second. If that frequency drifts too far from 60 hertz, generators and turbines can begin to vibrate violently. Left unchecked, those machines can suffer catastrophic damage in seconds. So the grid has a built-in survival strategy. If the system begins to destabilize, parts of the grid intentionally shut themselves off. Engineers call this load shedding. When a major disturbance hits, maybe a large power plant suddenly trips offline or a transmission line fails, the grid reacts instantly. Automated protection relays detect the imbalance. Within milliseconds, they begin disconnecting pieces of the network. Entire neighborhoods may go dark while nearby areas remain powered. From the outside, it looks random. The grid is reducing demand to avoid total failure. Sometimes this strategy works, but if the imbalance spreads faster than the grid can contain it, the problem cascades. Transmission lines overload. Generators automatically shut down to protect themselves. Sections of the grid separate from one another, and the blackout spreads. At first, many systems keep running. Cell towers typically have battery backups designed to last 2 to 4 hours. Internet infrastructure may continue operating briefly on backup power, but as the hours pass, those systems begin to fail. Cell towers start dropping offline one by one. Data centers switch to generators, but fuel logistics quickly become a concern, and suddenly millions of people are trying to use the same shrinking number of communication systems. Phone networks become overloaded. Emergency services struggle to respond. The digital world that normally connects us begins to fragment. Electricity also powers the machines that move water. Most cities rely on electric pumps to push water through treatment plants and into elevated storage towers. Those towers provide pressure so water can reach homes and businesses. But once the pumps stop running, the system begins to drain. Within hours, pressure drops, and within a day, towers can run dry. Faucets slow to a trickle or stop completely, and suddenly, something as simple as flushing a toilet becomes a challenge. Modern cities rely on what's known as just-in-time logistics. Instead of storing weeks of inventory, stores receive shipments constantly, sometimes daily. But the supply chain is powered by electricity. Gas stations can't pump fuel without it. Distribution centers can't load trucks. Warehouse automation shuts down. Even if fuel exists in underground tanks, it can't be accessed without electric pumps. Meanwhile, grocery stores face another problem: refrigeration. Without power, refrigerators and freezers begin warming and food spoilage accelerates rapidly. In just a couple of days, massive quantities of perishable food can be lost. Hospitals are one of the few places designed to survive grid failures. Nearly all major hospitals have diesel backup generators capable of running critical systems. Operating rooms, ventilators, and life support equipment can continue functioning. But those generators rely on a steady supply of fuel. And in a widespread blackout, refueling becomes extremely difficult. Fuel deliveries require trucks, trucks require diesel, and diesel requires functioning fuel infrastructure. Hospitals are prepared for outages measured in hours or days. A long-term blackout becomes a logistical battle. If this scenario sounds like science fiction, it isn't. We've seen versions of it before. In 2003, a seemingly small problem triggered one of the largest blackouts in history. A software alarm system at a control room in Ohio failed. Operators didn't realize transmission lines were overheating. Those lines sagged into nearby trees and shut down. The resulting cascade spread across multiple states and into Canada. Within minutes, 50 million people lost power. Cities like Cleveland, Detroit, Toronto, and New York went dark. The entire event began with a handful of unnoticed system failures, and it demonstrated how tightly interconnected the grid really is. But here's something most people don't realize. The electrical grid is so tightly synchronized that if the frequency drops just a fraction of a hertz too far, power plants begin shutting themselves down automatically. And once that cascade begins, operators may only have seconds to stop it. Another warning came in 2021 during the Texas winter storm. Extreme cold caused natural gas infrastructure to freeze. Power plants shut down faster than the grid could compensate. Demand surged as millions of homes turned on electric heaters. Because Texas operates largely as its own isolated grid, importing power from neighboring states was limited. Frequency on the grid began falling toward catastrophic levels. According to grid operators, the system came within 4 minutes and 37 seconds of a complete statewide collapse. If that had happened, restoring power could have taken weeks or even months. One of the most serious risks to the grid doesn't come from Earth at all. It comes from space. It's our sun. Occasionally, the sun releases enormous bursts of energy called coronal mass ejections. When these charged particles hit Earth's magnetic field, they can induce powerful electrical currents in long transmission lines. This phenomenon is known as a geomagnetic disturbance. The most famous example occurred in 1859 during the Carrington event. If a storm of that magnitude struck today, it could damage the extra high-voltage transformers that sit at the heart of our grid. These transformers are enormous and can weigh hundreds of tons. Many are custom-built, with replacement times measured in months or even years. Despite these risks, engineers aren't standing still. They are engineering the grid of the future. Next, we will explore the technologies that may make the grid more stable. If you enjoy learning about the hidden systems that keep our world running, take a second to subscribe to this channel. One of the most promising technologies being implemented is the microgrid. A microgrid is a small, self-contained power system, like those used on university campuses, hospitals, or military bases. Under normal conditions, it connects to the main grid. But during a failure, it can disconnect and operate independently using local generation like solar, natural gas, or batteries. Another critical tool is something called black start capability. Most power plants actually need electricity to start up. But certain facilities, often hydroelectric dams or specialized gas plants, can start themselves using small internal power sources. Once running, they provide the electricity needed to restart larger plants and rebuild the grid piece by piece. And increasingly, large grid-scale battery installations are being deployed. These lithium-ion systems can inject power into the grid within milliseconds, stabilizing frequency during disturbances. Think of them as shock absorbers for the electrical system. The electrical grid is often described as the machine that never stops. It operates continuously, balancing supply and demand every second of every day. And remarkably, it succeeds most of the time. In the United States, grid reliability averages better than 99.9% uptime. But as energy systems evolve, with more renewable power, electrified transportation, and increasing extreme weather events, the grid is entering a new era, and understanding how it works is the first step toward making it stronger. Because when the lights go out, we are reminded of something we usually forget. Electricity isn't just another utility. It's the foundation of the modern world.